These all belong to use a very small matrix theory to represent we use the basic method. Obviously, hopefully, what I will. Yeah. I can't really have the lobby since I have okay, so stuff in problems. So, but I'll come hang out because everything's cool.
Yeah.
Yeah, I mean, there's tons of stuff that sci-fi that you can find.
You should see.
This is the whole reason to do to make the video.
Okay, we'll start the second morning session with Chinmay Mishra from University of Tennessee, Knoxville, and he'll talk about a nuclear mass model rooted in chiral effective field theory.
Hello, everyone. So I'll talk about ongoing work which is being done in collaboration with Andreas Ekstrom, Kalte Hagen, and Thomas Papenbrock. And feel free to ask me questions in the middle of the talk or at the end. I'll start with a brief summary as to what the job of nuclear mass models is. The task is to come up with predictions for nuclear binding energies, and it has had a long history, going all the way back in 1935, let's say, with Weizsäcker's model, and here we're looking at a modified version with an additional term. But the basic idea, we have predictions of nuclear binding energies given the number of protons and the number of neutrons. And the binding energy is expressed as a sum of volume term, surface term, Coulomb contribution, asymmetry, and later on pairing as well. So nuclear mass models, excellent nuclear mass models already exist today. So here we're looking at two examples on the right, where the root mean square deviation is half an MeV. The one at the top is the work by Moller and co-authors, which is based on the finite range droplet model. And the one at the bottom is a Hartree-Fock-Boville calculation by Corelli and co-authors. And we see that in each of these cases, the root mean square deviation is half an MeV. However, often a direct connection to quantum chromodynamics or chiral effective field theory is often lacking in nuclear mass models. There are exceptions, of course. Here I list a few, and show in particular the work by Zurich and co-authors, where they take their density functionals and supplement them with contributions from chiral effective field theory. And in particular, they report that they find improvements significant improvements after going to next to leading order, including delta and 3 influences. Right. So one additional piece of motivation for this work was the observation by Zhonghao Sun and co-authors in 2022, where they carried out a couple of cluster calculations using singles and doubles excitations only. But they renormalized the three body contact, CE, to reproduce oxygen 16 binding energy, right? And then they found that the resulting renormalized interaction extrapolates pretty well compared to the exact, compared to the reference, which was couple cluster including singles, doubles, and triples excitations across 6 additional nuclei. So motivated by that, we wanted to ask the question, we wanted to explore whether it is possible to start with a chiral interaction and renormalize the short range contacts, the low energy coefficients in the interactions so as to accurately describe nuclear binding energies. So the interaction we're working with is shown on the left here. It's represented as a hierarchy of exchanges, hierarchy of interactions involving nucleons and pions. For example, at the leading order, solid lines represent nucleons and dashed lines represent pions being exchanged. So at the leading order, we have 1 pion exchange and a short range contact, which accounts for the accounts for our ignorance of the high energy details that are not captured by chiral effective field theory. At next to leading order, we have once again nucleons exchanging pions, this time 2 pions. And instead of 2, we have 7 unknown short range coefficients here. There's also delta excitations. And lastly, at next to leading order, we have further 2 pion exchange diagrams, and for the first time, 3 Gaudy forces as well. Right, so the goal is to tune these highlighted low energy coefficients so as to accurately, at least in a schematic sense here, capture the nuclear binding energies. So before I get to the specifics, I will spend one slide introducing the nuclear shell model for anyone who's unaware of it. So quite in close analogy with atomic physics, nuclei also exhibit shell structure. The crucial difference is that unlike atomic physics, where the Coulomb force is the origin of the shell structure there, unlike that case, in nuclear physics, we have shell structure as a result of the average interaction that any given nucleon feels from all the remaining nucleons in the nucleus. Right, and this emergent mean field serves as the bedrock for a lot of microscopic mass models. And here, just to cement that analogy of the shell model with atomic physics, we are looking at a harmonic oscillator potential with an additional spin orbit term added to it. And we have shell structure and magic numbers are also captured until 50 here, in the simple oscillator model. The image is taken from Wikipedia. So the task of finding the binding energy is essentially a task of solving for the ground state of a large complicated Hamiltonian. So so if we have access to an infinitely powerful supercomputer, we would just put in QCD or chiral effective field theory and extract out the ground state energy, and that would be the binding energy of the nucleus. We have various truncations and finite computers. So we solve here by taking we solve for the binding energy by taking the approximation of the mean field. So we don't consider correlations and so forth. And we work in a model space which has 572 single particle orbitals for neutrons, as well as for protons in addition. All right. So with that background, here is the optimization problem that constructing a mass model amounts to. Right. So it's a nonlinear least squares problem represented here on the right. And we have, in our case, 18 nuclei that we want to learn, that we want the objective function to learn. And we want to minimize these individual residuals as a function of these 11 LECs, 11 unknowns that we saw a few slides ago. All right, so the training set has 18 nuclei that we chose. It's a combination of spherical and deformed nuclei, including neutron-rich ones, neutron-rich nuclei. But due to the model space that we looked at in the previous slide, this task of performing Hartree-Fock calculations for optimization is prohibitively expensive, and we wanted to avoid having to build a system that calculates and reads in all the data, all the matrix elements in real time as each objective function evaluation is needed. So we make use of model order reduction to create fast Hartree-Fock emulators. And we basically start, and that process is represented schematically on the right. So we have an 11-dimensional space, which is the space spanned by, which is a space in which the set of low energy coefficients lives. And the interaction, delta into a low interaction that I'm working with it corresponds to a specific point in the space, right? So the values of the LECs correspond to this point here. And the idea is to sort of learn the analytic structure of the space around the central point, and then use that to create a fast emulator. Right, so we take a 10% neighborhood in the vicinity of the central point and take a small number of pseudo-randomly sample points and solve Hartree-Fock equations numerically exactly there. Right, these are the snapshots that we've heard about today. Once we have exact solutions after carrying out expensive calculations, once we have exact solutions at these points, we can project out a smaller subspace. And here I'm taking a picture from the review by Today and co-authors present here. And the idea is to collect all the exact solutions shown here. And this first stage was expensive, as we saw on the previous slide, but we can construct, using these solutions, a smaller projected subspace, which allows fast emulation of Hartree-Fock energies. How fast? And the answer to that is, it takes only a couple of milliseconds for me to do this, evaluate the Hartree-Fock energy given a random set of LECs on my laptop. This involves.
I think I may have missed a point. The red point in the previous slide, I thought that you were searching for that point. You already assumed that you know that point?
No, so this red point here corresponds to, in some sense, an unrenormalized interaction that we're starting with.
Okay.
Yeah. I have a table here. So the red point corresponds to the LEC that defines this interaction.
Thank you.
All right.
This seems extremely reminiscent of eigenvector continuation.
It is, yeah. That's exactly what it is.
Like, just making
Yeah. It's an application. Yeah.
I must have missed it. My bad.
No, that's fine. All right, so we have a small dimensional projected subspace which allows rapid, which is essentially a reduced basis model, reduced basis Hartree-Fock model that we can use. So we construct this emulator, and then it's useful to see how well it performs. And here I'm showing you a validation result. The validation results for an emulator constructed for nickel 56. And I'm plotting along the x-axis, along the horizontal axis, exact Hartree-Fock energies from 200 calculations performed at 200 randomly chosen points in this neighborhood. And along the y-axis, I'm plotting the errors in the emulator. And we see that, especially in the region of interest, the emulator is 0.1%. In agreement to 0.1% with the exact calculations, and this is good enough for our task. It is also good to notice that nickel 56, which has a binding energy close to 500 MeVs, is somehow represented in this neighborhood here, because we have a substantial density of points that corresponds to roughly 500 MeVs of binding. Right, so this is one emulator, and we repeat this game. We construct emulators for 17 other nuclei that are present in the objective function. And as a reminder of what the problem was to begin with, we were trying to solve this optimization problem, this nonlinear least squares problem. And seen as a function of the LECs, the Hartree-Fock energy was being optimized for, right? So the emulators we have constructed facilitate fast evaluation of these residuals, and we find an optimal point within this 10% box around the central point. There is a little caveat, an exception. So, okay, in this table, we are looking at the first column is the set of independent variables for the purpose of this problem, and they correspond respectively to leading order and next to leading order and next to leading order short range contacts in this interaction. And in the second column, we have the set of LECs that defines the interaction, the red point that we talked about. And this column represents one of the optimal points that we found. The exception is the last cluster here, where the LECs initially in the interaction were rather unnaturally small. So we expanded the search radius and the emulator construction there to construct so that in these two directions, size one, order one values are scanned. Right, and so as a result, in the optimal interaction, we have somewhat natural values, and that's also good.
Was your search radius beyond -0 or -2, or and it just happened to be 2 to 4 significant figures, or was that the end of the search radius?
That's the end of the search radius. So it is at the boundary, but we don't want to extrapolate for some reasons. But yeah, it is at the boundary. Good observation. Right. How am I doing on the time?
You're fine. You've 15 minutes in.
Okay. So at this optimal point, we can now go and ask what is the objective function? What do these residuals look like? And that is what we're looking at in this plot. Along the x-axis, we have these 18 nuclei, which are being optimized over. Along the y-axis, we're looking at binding energy per nucleon in units of MeV. And for each nucleus, the black bar, the third bar for each nucleus represents the experimentally known binding energy per nucleon. And the red bar represents the Hartree-Fock energy at that red dot at the center we looked at. And we see that in each of these cases, for each of these nuclei, we are missing about half of the binding per nucleon. So about 4 MeVs of binding is missing. And in the blue bars, in the second bar for each nucleus, we see that after renormalizing these LECs as described in the previous slides, the Hartree-Fock energy tracks very closely the true binding energy.
Maybe I'm missing something. On the previous slide, when you showed the parameters, the center and the optimum, they don't look like they change very much. But this is a very large change in the binding energy. Can you help me see what I'm missing?
So the small variation here is kind of by construction. So we constructed a 10% neighborhood and sort of learned the first derivative, second derivative, loosely speaking. And so we stay within this box. But you're right, the gains in terms of binding energy looks rather substantial.
And just with respect to that, we talk about hitting the edge of the box, so it was happy to be within 10% for all those parameters except for the 3 bound. It found it out.
Oh, so there were multiple. So if I understood the question correctly, there were multiple points which are hitting the box, but we don't want to extrapolate because there were errors in the emulator as we go farther out of this 10% radius. So this point already is outside the interpolation regime proceeding.
But are any of the other ones or most of them at the edges? I guess if you said 10%, they do look like most of them are 10% away.
So I think at least 3 or 4 of these are at the boundary. Yeah.
Why, if it's a Hartree-Fock, why did you stop at nickel 56? Why not heavier?
Sorry, why not?
Why not heavier nuclide than nickel 56?
It was just a choice that we made because initially we were not. So nickel 56 is the heaviest element that we have in the objective function that we construct an emulator for. And we did not want to
You don't
explore,
like lead?
no, no.
But I mean, would that present more challenges within the Hartree Fox scheme?
On space.
Challenges.
Yeah,
Everybody next to us.
Okay, thank you.
Ellie?
So maybe I missed it, but did you show the couple cluster results for the untuned unemployment for the city? Yeah. I think you should have the pop results for the untuned unemployment.
You mean this plot? A previous work or something that I showed from ongoing?
Oh, no, when you compare, when you have the vertical bars, like.
I see, this
Yeah,
one?
so here, what, hypothetically, if you could add for a few nuclei, right, not for everybody, but say for closed shell, say for oxygen 16. Where will the full couple cluster with delta and then will go be?
So I have not carried out this question, this calculation, I'm interested.
But I think it's very.
It's pretty close to explain.
So for say, for all nuclei that you can do couple cluster, it's very close to experiments and to the group. So basically, one can say that including correlations amounts to basically normalizing the three-body force because the
Yeah,
three-body force
yeah.
doesn't change much.
Yes,
Okay.
yeah, so I'll just comment on that point that the missing energy here is captured by higher order methods. In particular, for example, we were talking about couple cluster. So all of this energy, most of this energy is indeed captured by couple cluster singles and doubles and triples then thereafter without renormalization. So this process going from red bar to the blue bar amounts to kind of saying that the binding is being driven after this renormalization, binding is being driven by the short range ingredients of the interaction. Right. So the root mean square deviation on the set of learned nuclei is 2.2 MeV. And how does it generalize? How does it generalize to nuclei outside the training set? And here that we're looking at the results for that. We're looking at the nuclear charge restricted to 56 particle number, and the lightest one being oxygen 16. And all the results that all the nuclei that are included that we just looked at in the previous slide are the circular plot markers, and the results for extrapolation are the 89 square plot markers. And we see that most of the region here is pretty good, and the root mean square deviation is about 3.6 MeVs here. That's my talk here are the key takeaways. So this represents our first steps towards building a mass model that is based on Hamiltonian methods, connected to chiral effective field theory and renormalization. And we do this by renormalizing 2 and 3 nucleon short range contacts to reproduce binding energies, to learn binding energies of 18 nuclei. And then the root mean square deviations on the training and test sets are respectively 2.2 and 3.6 MeVs. Thank you.
I'm still stuck on this search hitting the search boundaries.
Yeah.
So you said this is limited because your emulator kind of fails past.
Yeah, yes.
Okay, so when you do a search a constrained search and you hit the boundary, you run into lots of problems in terms of now you don't actually know you have an optimal solution. U2 becomes borderline impossible sometimes. Why not add more basis states to your eigenvector continuation to make that emulator work and actually be able to do a quantifiably rigorous optimization?
Yeah, so to respond to your first comment about we are not at an optimal point. So that is true. So in the sense that let's say there's a family of optimal points, we have not reached it. But the statement we're making here is that this is as close as we've gotten to it. And your second point was why not just increase the size of the projected subspace? And there, I think it's going to be more a matter of expanding the region that is being learned. But I have not analyzed that.
If you could take your optimized one and make it the new red point and do the same thing again.
Yeah, definitely. So in the initial stages, we were somewhat apprehensive to do that because. Okay, so at the very beginning, we were not restricting to this 10% radius. But we wanted, in the end, we decided that we wanted to be close to the central point because that is a point that we understand. That is a point that we understand in the sense that it has been tuned to other properties of light nuclei and nucleon-nucleon scattering. We decided that we want to stay close to that.
If I may propose a suggestion, instead of hard boundaries, you can add a penalty for moving farther away from this point, something smooth.
Yes.
And it might help. I don't.
Sebastian, do you have a question?
Yeah, but that same point, so it was pretty fine tuned, right? So even the 10% radius in terms of the parameter space around that, you might already be losing quite a bit of that fine tuning in like, opt or whatever the reference point was, don't you? I mean, what does it mean to be within 10% for in this 11-dimensional space? Like if you were just to plot the variation over, like, say, just grounded energies across that whole space, like, are you actually even close in any physical sense to that potential?
I see. Yeah. So.
Yeah, right. Yeah.
So we are close. Only in the sense that, okay, as we say, most of the binding energies stay close to 250. So 250 was we're lacking half the binding energy without renormalizing the coefficients. So most of these points cluster, let's say, close to 250. But yeah, it's an 11-dimensional space, and the best we do is scan 10% boxes in each of the first 9 directions.
And that gives you, for nickel, it gives you this kind of spread.
Yes.
So in that sense, this 10% is actually huge.
Yeah.
Right.
Oh, definitely. Yeah.
That's what I'm
Yeah.
And Sheila?
Go ahead. Me? Oh, okay. So first, brief comment. We talked before about this, but I think doing this proper orthogonal decomposition
Yeah.
could give you a little more bang for your buck if you consider this high dimensional space. And give you better convergence as a number, as a function of basis. So that's something that could be potentially good for your emulator, if you would consider it.
Do you anticipate that it would have an effect on the extrapolation as well? Outside this?
Potentially, it's kind of hard to say, but at least it should be more efficient than just a basis of snapshots alone, because you can inform it from more snapshots while still having more of these spaces.
Right, true.
So, but that's the comment. The question is more on the observable side. So I know you're focused on a mass model, so I shouldn't expect it to do good for other observables perhaps, but did you check out things like charge radii or observables?
No, I have not done that.
Okay.
It's on the radar. Sorry.
I'd be very curious about like if it's tracking.
Yeah, me too.
Sheila?
Maybe you have to explain in the beginning about analysis. My understanding that Hashbox solution is a minimization problem, but within a constrained subspace. So you assume the solution is one slightly determined. So now-
Yes,
yeah,
yes.
Now when you do like the training, each one solution is a one slightly determinant. And when you do emulation at one particular emulation point, the solution will be a sum of different slightly determinant. So is that still a Hashbox solution to that particular component?
Yeah, so I hope I'm understanding the question correctly. So we obtain this optimal point, and then these results are exact Hartree-Fock calculations using one Slater determinant.
Yeah, the training point. Yeah. But when you do at emulation point,
Again.
Yeah.
So basically GCM, you say. So we're not doing GCM there.
Exactly.
We're taking on a one body part for two body. If we would include the two body part, we would actually get energies that are lower than we
Right.
accept the Fock
right.
calculation. So that's the GCM. analogy, right, which we are not doing, because we want to keep the long way. Long way limit. So you never get lower than the accepts.
It's guaranteed that you are actually emulating happy box.
Exactly.
Yeah, give it.
So if I can add one Carrie's question. If you ever generalize your model to have the radius, you could maybe see the effect of this renormalization on the radius. Because it seems that it's a way to take into account beyond mean field correlations, and it has only an effect on three body forces where it is significant.
Yeah.
And this should be related to the radius.
Ali.
So I maybe that's not the philosophy of the talk about. Can you fit the mass? Say you have an effective mass instead of giving it to the actual value, because in nuclear matter, if I were to use say an effective interaction rather than the bare one, I would use the effective mass as an random parameter instead. So it's something that I can choose, but my passive particle is captures some of the correlation effects. So can you add it to the set of parameters that you optimize, or is it feasible?
Sorry, I don't think I followed the question. Can you repeat what can be added to the set of parameters?
I'm instead of giving the mass x to the nuclear mass,
Yeah.
consider an effective mass. So
I
you're
see.
changing the mass by 10%.
I see, yeah.
Yeah, because in nuclear matter, basically you have effective masses like typically smaller than one. If you try to, I mean, within a mean, how can I say that? Within a Landau Fermi liquid theory. So I was thinking that this is, nuclear, if you see this effect, the actual nuclear.
Hopefully wants to say something.
Can I have
Yeah,
one minute?
yeah, sure.
So just to follow with the comment with Karen, because I think a picture that I cannot show because it's in there will help with the orthogonalizing or non-orthogonalizing things. I like to think it this way, that you have the manifold of solution that is moving in your high dimensional space. And if you just construct your bases using snapshots, it's kind of like 2 points, 2 exact points in that manifold, and trying to fit your reduced model around that. So this is going to be relatively good for interpolation in there, but not necessarily going to extrapolate as well as if you were to say, I'm going to put many points in my manifold, and I cannot pass through all of them, but I'm trying to find kind of the smallest linear space that encompass all of the things that I saw. I think there are proofs out there that show that this is the case, but this is a geometrical way of motivating why it's usually a good idea to have many if you can, and then do PCA.
This is Scott had.
Yeah, I was just wondering, have you computed nuclear matter?
No, I have not.
Would you give inside your?
That's a good question.
Yeah, I mean, it's a question about radiation.
Okay, one last question, Yanja.
So, have you ever draw some plot to see the correlation from different terms of your parameterization? So maybe from that we can get some information as the hypercube level. For example, the two-body force or the three-body force will take the responsibility for this and the difference.
Yeah, so unfortunately, I don't have that plot here, but in that plot, the largest contributions do come from the leading 1s0 and 3s0 contacts. Yeah, but I don't have it here, that plot.
All right, let's thank Chinmay once again for.
Oh, green good. Okay. I think it's very nice. Yeah. But I thought you literally were like, common type reason.
I would never disagree.
All right, our next speaker is Simon Sundberg from Ohio State, and he'll be talking about criticality analysis of artificial neural networks in nuclear physics.
Hi, everybody. It's good to be here.
So yeah, I'm gonna be talking about artificial neural networks and nuclear physics and doing some really interesting stuff with statistics on them. So as we all probably know at this point, machine learning is extremely important to the scientific process. It gives us all sorts of new ways to look at nuclear systems in ways we haven't done before and improve methods for analyzing them that already exist as well. And that's basically why we're all here. And in my particular focus, I'm interested in applying neural networks in nuclear physics and understanding how they work and how to best apply them. And so I have some examples of interesting applications of neural networks within nuclear physics. This first one is from Wolfgruber and collaborators, and it's basically an application to no-core shell model. Basically, as you increase your model space, well, we don't want to laser point. What's going to end up happening is that the computational time is going to increase for these no-core shell model calculations for various observables. And so rather than do the full expensive calculation, what they're going to do is notice that there is a convergence pattern and feed this data to a neural network and then use that to predict what the converged observable that we care about, the radius or a binding energy or whatever we are interested in. And so another one, which is actually done by Ali Lovato and collaborators, so you can learn more about this tomorrow when he talks about it, is neural network with quantum states. The idea being that we're using neural networks to learn more efficient ways of calculating wave functions and densities for nuclear systems by taking different inputs and then getting this output here. And on that note, there's also been some work done with neural network quantum states where rather than looking at how to get larger, looking at larger nuclei, instead looking at simpler cases like a deuteron wave function here, but testing different architectures to see which best learns the different wave functions in terms of how accurate the wave functions are and how accurate the ground state energies are for them, either with one layer or two layers, or looking at learning the S and D ground states separately. So there's a lot of different things that we're looking at with neural networks and nuclear physics. They're all very interesting, and we're trying to learn the best way to construct our neural networks so that they can do the job that they're supposed to do. And so what I'm interested in then is figuring out how to best construct neural networks and making them less mysterious, less of a black box that we put stuff into and get stuff out of. So the idea with a given neural network, for those who are unfamiliar, is we have some input X down here that we feed forward or up on this diagram into the neural network. And that's going to end up getting multiplied by a matrix of random numbers called the weights, which carries it to a vector here. And all of the elements of this vector, which is known as a layer, these elements are known as nodes or neurons. And essentially the matrix multiplied input has a bias, which is another vector of random numbers added to it, which then gives us what's known as a pre-activation Z. That gets acted on by an activation function sigma, which then passes another output to the next several layers and continues on this until we get a final output. Yes.
So you don't actually mean random, right? You just mean it's going to be determined by the training.
No, so before we do training.
Before the training is random.
Yes,
Because
your
you
initial.
don't put them to one, right? It's arbitrary.
Right. So the idea is that these lines here represent all of those different weights and biases. And the idea is that when we start, before we do training, they're initialized according to some distribution that we're allowed to select, basically to get random numbers, so that when we go to training, we can adjust those numbers and get the specific configuration that gives us our functional relationship that we're interested in. Yeah, so the idea though is that when we're doing this, rather than caring about all of the individual parameters, what we do to actually set up this architecture and actually set up our neural networks is we have to specify hyperparameters that govern, how we lay out all the parameters. And those basically are things like the depth, which is the number of layers stacked on top of each other, the width, which is the number of nodes that we have in the given layer, and then the activation function, which actually determines how the different information is passed through the neural network. So that's all fine and good, but as of now, we're just getting a random output rather than a specific functional relationship. We actually have to train this thing. So this is the other half of it, basically, is that we get some random output, and then what we're going to do is back propagate through the network and parameterize a cost function or a loss function, which I called C here. The idea being that that cost function will parameterize the difference between whatever output we have and whatever output we want to have for the functional relationship.
And the way that we get what we want is we minimize that cost function. We do that usually through a gradient descent algorithm, where we adjust all of our different parameters, the weights and biases, until we've minimized that function. Problem though that we can have is, depending on how we initialize our weights and biases, and depending on how we set up the actual shape of the neural network, we can get some instability in the gradients. They can either be too large or too small, and so we never reach a true minimum and never have successful training. And so usually the way that this gets remedied is by either adjusting the different hyperparameters until you have successful training, which is what a lot of people will do in practice, or there's other methods of searching for architectures. But the gist is that currently we are adjusting these hyperparameters until we get something that works, and it works magnificently. We've got a lot of great results, but is there a more systematic way of doing that? And so the whole point of this talk is talking about using statistics and perspectives from field theory to actually find the best way to set up a neural network architecture so that we can not have to worry about tweaking different hyperparameters and just get it from the go. So the goal is, if we're trying to train this thing, we're trying to get a functional output that has some input X that we care about and some set of parameters we want to reach that depends on whatever data that we have. And we want to get a probability distribution because we have all these different random initializations that we're then training to reach whatever desired result. And so what we're going to do is, starting from the perspective of the probability distributions for the weights and biases, shift from that perspective, those as our parameters, to looking at the actual outputs that we care about at a given layer, and looking eventually at the final output that we have. So all of this stuff right now is before training. It's just when we're dealing with randomly setting up weights and biases. So for a given layer, you're going to have these outputs, these pre-activation Z, where we're summing over the matrix multiplied input from the previous layer and a bias. And what's going to end up happening is, if we sum over all of those things and look at what's going on with our variables in further layers, what's going to end up happening is we'll have a statistical distribution if we're initializing a bunch of times with random numbers, that if we condition these just right, central limit theorem says that our outputs that we're going to have, our probability distributions for these guys, are going to look like Gaussians. So if we consider a distribution essentially where we're starting with some initialization and trying to get to some final trained result, the idea is that we're looking at our final trained guy as a perturbation theory, where we're doing kind of a tailored expansion about our initialization setup. So to kind of contextualize that further, if we want to set up all of these different outputs that are going to be sums of a bunch of random numbers, the thing that's going to end up happening is we can basically look at this through the lens of a central limit theorem, as the width up here gets very, very large. And so if we look at different correlations and things from probability distributions for these guys, we can end up calculating these from central limit theorem and calculating them diagrammatically like we would in field theory. So looking at like a 2-point correlator where we're looking at two different neurons in a layer interacting. The idea is we can also do higher order moments of interest too. So looking at correlations between 4 different outputs in a given layer. And so we have like contributions from a vertex and contributions from products of different 2-point correlators before. And if we take the infinite width limit, what ends up happening is all of the vertices here disappear and we only get contributions from 2-point correlators. So the thing that's interesting about this is that this is a free field theory. It's a Gaussian probability distribution. And so when we go forward, we can basically calculate these types of observables like we would in quantum field theory. And if we back off of this infinite width limit, we can start to reintroduce vertices and interactions and calculate that like a quantum field theory with perturbation theory. Yes.
Question. So all this, does this claim depend on the way you set up the prior distribution for those parameter weights?
You're referring to
the independent Gaussian?
You're referring to like these distributions and then how they establish those.
There's no correlation between those weights
Mhm.
and offset.
Right. The idea being that all of the outputs, the pre-activations that we care about are gonna end up having to be independently and identically distributed, have a mean zero and have some variance essentially, so that when we take this infinite width limit in the next layer, central limit theorem can actually kick in and we can get the distributions that we care about, yes. Yeah.
Do you need to assume any distribution about the actual input? Say, suppose that you have the first layer, okay, so instead of sigma j, we have x, which is the input. If x is not Gaussian, but say it's completely very large and negative,
Mhm.
will the output of the first layer be Gaussian distributed if the width of the net goes to infinity, independent of the input or not?
So from the analysis that I've done, I've basically assumed that the inputs are deterministically specified so far. So essentially you have a collection of elements that are all just independent, either scalar numbers or vectors, whichever you care about. But the distribution for the first layer pre-activation, so if you had like an architecture where you're going to that first layer, those basically, given the Gaussian initialization for the weights and biases, will give you a Gaussian distribution for the pre-activations in the first layer that gets more correlated.
So IID times other things are still IID. It doesn't have to be Gaussian, it just has to be IID.
Independently and identically distributed.
Identically distributed.
So if I say, if my inputs are, let's say, -1,000, would that the output of the first layer, and W is Gaussian, D is Gaussian, they're all independent, and would Z still be a Gaussian
Yes, in the first layer,
in the first layer as well?
yes.
The W's are Gaussians, and then the inputs will just be
Yeah,
linear combination of Gaussians.
so these are Gaussian, these are Gaussian, in the
And it
very.
actually doesn't matter as long as there are any IID distribution, because central limit theorem would say, okay.
Thanks.
So yeah, anyways, the idea is that in this infinite width limit, what we get is a free field theory, essentially, where we only have 2-point correlators and their products making up all of the relevant moments. And as we back off of that, we can start doing perturbation theory in terms of interactions between different neurons or nodes in the layers and start calculating observables exactly like we would in field theory with like path intervals. So again, to kind of get the big picture, this is kind of a formalism that a lot of people have been developing, but we're going from this idea of working with weights and biases and now just transforming it so that we're working with the actual functions, the actual outputs, and seeing what they're doing in terms of the field theory. And so, again, we can do all of this kind of stuff diagrammatically, where we're looking at all of the different correlations and things of interest at a given layer and introducing more interactions. And so again, just to kind of recap, the idea is we have some starting initialization, which is this theta, and we want to get this trained function and get a distribution for that. And we're basically just treating this as a Taylor expansion about this initialization. What ends up happening though is that there are ways of, by tuning the architecture in the right way, suppressing these higher order terms in the Taylor series so that we only have to worry about a finite number of things that are of interest to us. So going back to the kind of field theory perspective, then, if the infinite width limit gives us a Gaussian, which is a free field theory, you can basically then go and write other types of probability distributions based on how we've initialized this neural network that will have, you know, a Gaussian term and then other higher order interactions that are suppressed by increasing powers of n. And so as long as we have a sufficiently wide width, we can suppress certain types of interactions and only have to worry about a finite set of couplings that determine the strengths of these different types of interactions, being the Gaussian or the quartic or any higher that we can include or want to include. The other thing though is I've been talking a lot about the width. There's also the depth as a relevant factor. That's what this index L is here. That's what layer we're in. The interesting thing about the width is that as you move forward in the layers, it exhibits a behavior in these couplings that behaves not unlike a normalization group flow. And so the idea here is that these couplings will either grow or shrink or stay the same as we move further into the layers. And so what we want to basically do is, in order to get stable training, in order to make it so that we're avoiding these issues where we've set up a neural network and have to tweak it, we can basically find fixed points in these couplings under the further in, like going through all the further layers, such that we can avoid these kind of gradient issues, because the gradients end up depending on the magnitude of the different outputs. And so all of these different couplings will have a recursion relation that you can calculate with the layers, and you want to try to find different initialization widths of the distributions so that you can get this coupling to be stable and then have stable training. So that was my laser pointer. But so I did this for a couple different examples. The first one was just a linear activation function. So this means that my neural network, which has 3 hidden layers, 1 output layer, just has matrix multiplication going on. There's no activation function actually screening the information. And so, well, I guess you could say the identity is a more accurate way to put that. So that's there. But the idea is that if I keep it at this fixed depth and I increase the width from having 1 node per layer to 25 to 120, what you can see is we go from a distribution that is not Gaussian for the output. So this is a scalar input, scalar output, to something that is more Gaussian. Yes.
You probably explain it, and I got lost. What in here, what is the source of randomness? Is that every point you're initializing is a new network?
Yes, so the idea is same network shape.
Yes.
But I am changing I'm reinitializing and getting new random weights and biases every time, and then seeing what my functional output looks like before training.
What do you do with the input? Well, once you have one network in there.
I'm using the same input. So this is, I think for this one, just for the heck of it, I used pi squared as a scalar number to plug in, and then did it for a bunch of initializations.
Perfect.
Yes.
Thank you.
Just for clarification, the black curve, is it actually exactly the same in all plots, or how was the black curve determined?
So the idea is that I have, for all of these 100,000 different initializations that have the various outputs, and I took those distributions and I calculated the mean and the standard deviation, and I calculated I made it have a Gaussian basically fit to this to show this is my actual distribution as the histogram, and then this is a Gaussian fit to it, showing that with this particular mean and variance, this is what a Gaussian of that would look like, and this is what my actual distribution would look like. And so as I increase the width from 1 to 120, we go from something that is not a Gaussian to something that is basically a Gaussian up to some fluctuations. And so the thing that's of interest then is you can go and do this with the depth as well, and look at these outputs and look at the variance of the output distributions. And what you can see basically is that I took a neural network where in all these neural networks, they have 50 nodes in every layer. And I basically then just increase the depth. And so what ends up happening basically is that this linear network has a fixed point for its 2-point coupling. It's this, if you set the variances for the distributions for initializing weights and biases to these values, you will get a stable output. If you set it above, basically what you're going to get is that with every increasing layer, the output variance, aka the 2-point coupling, is going to get bigger. If it's below, it's going to get smaller. And if it's at criticality, it's going to be stable.
Can I interpret this as feedback from a microphone and a speaker? Like is the right way of thinking it, that as the network is progressing, if you have something that is amplifying the
Yes. Yeah.
Okay.
So basically, as the network, as the information goes further through, it keep the coupling that you have at that given layer will get bigger. Yep. And it gets bigger exponentially.
Sorry, maybe I've lost track, but have you made any assumptions about the activation function?
That's so the only activation function assumption is that
That's right.
an identity.
Like I said,
There's 2 more quick ones. This is the long bit, but the exciting thing though is that we get stable outputs, and that means stable training, which is great. Now we're going to do a ReLU, because the thing about the ReLU that's exciting is that it has the same type of non-Gaussian to Gaussian behavior as I increase the width and keep it at that same depth. It also has a fixed point, which is very, very exciting. And it belongs to the same universality class as the linear activation function. So again, if I'm above this critical initialization, it's going to explode. If I'm below, it'll vanish. If I'm at it, I'm going to have a stable output. And then I also did this for a soft plus activation function, which is basically meant to be a ReLU, but smoothed out so that it's a continuous function rather than a piecewise function. The thing about this is that it has the same Gaussian non-Gaussian behavior, or as the width increases, it becomes more and more Gaussian, indicating that the perturbation theory is an okay thing to do when we're doing these calculations. But it doesn't actually have a fixed point in its 2-point coupling, which means that regardless of what I do, if I tune it in a certain regime, it's going to be exploding in terms of the coupling, or it's going to be vanishing. There's no stable point in between. It just has like a crossover where it just switches. So the thing that happens there is that it just tells us that in practice, we see the ReLUs better than the soft plus for training. And this is another addition to why that might be.
It sounds like there might be a theorem that like if the activation function satisfies this under all these other assumptions, then there exists a fixed point. Have you explored that mathematically?
So there is, I have some citations at the end that have an in-depth discussion on this. They basically lay out some criteria that are where you can basically extrapolate which ones will admit a fixed point and which ones won't. But
you know how rigorous, like is there like a rigorous math theorem that says under those assumptions there exists a fixed point?
I haven't looked into a rigorous theorem. They've mainly done it through like a search algorithm for the different fixed points that are relevant and basically seeing, is there an actual possibility given the criteria that CB and CW have to be bigger than 0? And basically searching through and trying to figure out, does this point exist where we don't have any change in the recursion relation anymore, where it's stable? But they basically noticed some common features amongst the different styles of activation functions. So that's basically the extent that I know. I don't know about a formal proof yet, but that's something to do.
So
Yeah.
by doing say techniques like normalization, or does it automatically enforce that the weights are distributed, the output of the G is distributed like GL plus 1 is distributed the same as GL?
Oh, so yeah, so as you go forward in the, so the idea is that this recursion relation here, basically this sigma is the activation function acting on the pre-activation in a given layer. So we're looking at the distribution of outputs Z here, and then it gets acted on by this activation function. The idea is that in the very first layer, without fail, if you're setting this up according to those Gaussian initializations, there will be a Gaussian distribution for the first layer. Past that point, because your coupling is evolving according to this, where you're incorporating these different expectation values with the activation function, you will start to get fluctuations in terms of your variance in other moments. So the distributions will have the same form in terms of like they'll have a 2-point and then a 4-point and then even order moments, but the couplings themselves will change according to this.
Oh yeah, I'm saying, but if you say to weight normalization, like layer normalizations, this kind of techniques that have been used to improve the speed of the training,
Okay.
can you interpret them as putting back the fixed point in a sense? Because in that case, you're kind of enforcing that the distribution in L plus of GL, you know, that the distribution stays as Gaussian as possible across all layers.
No, I think that's a reasonable assumption. Yeah, I think. So you're saying basically rather than dealing with setting this up from the get-go, having methods that will adjust and normalize it in the given layers and basically.
That's what people do with say.
Yeah, so I would view it as this is another way of looking at how to do that that's coming from the statistics and from this field theory perspective.
One other thing, I understand why in your expansion you have like at first thought that you keep the coupling between 2 points in the same layer, but the one from one layer to the one before or after it are suppressed.
So the idea is that when you're doing these correlations, you're only looking at correlations between neurons in the same layer.
It's like same time correlations.
So in terms of the layer being like an RG flow parameter or an RG flow time or something like that, the idea, the kind of perspective, if you're looking at these as like fields, is viewing them as like 0 plus 0.
I was really thinking about quantum field theory, so I was thinking about correlation functions, same time correlation functions rather than different time correlation functions.
Yeah, so if you're looking at them in a given layer, it's looking at it as basically the same time correlation function.
But you're not saying that different layers are different spaces. I don't think that the term time and space applies to that.
No, it's a 0 plus 0 D field theory.
Yeah.
So that it's everything is happening basically in the same point. Yeah.
I have a question. So if if the system becomes unstable.
Yes.
with bigger variance, that actually means that the neural net actually provide you can search for more functions.
So what it'll do is it will give you the final output will have, if you're initializing it a bunch of. If you're initializing it a bunch of times and you're seeing that as you make it deeper, the variance increases, you're having more potential values that you can reach. The problem is that you're getting a very, very wide amount of points and some of which are very, very large. So when you go back to do that back propagation to train it, all of the training gradients and stuff will end up being proportional to the size of your outputs that you're looking at there. And so you might be stepping and adjusting it too much or too little, depending on whether it's exploding or vanishing. So the gist is that you still you'll have a wide range of functions that you can search through, but you won't necessarily be able to converge to any particular one function. So the training won't be affected.
Because the way you do learning, and because the way you do back propagation, that limits you.
Mhm.
That the validity of this minimization limits you to deal with all these stable configurations and not unstable configurations.
Yeah,
But in principle, unstable configuration allow you to search for more functions.
sure. It's just that you'll never arrive at a
It
function.
doesn't-
So it doesn't. It won't work. You'll be searching forever because it never converges to a minimum. And then some other things of interest are basically, all of this stuff with. We're looking at functions, we're drawing them from random distributions, and we've already talked about if I take an infinite width limit. Then it becomes drawing functions from a Gaussian distribution, and that is exactly a Gaussian process. One of the interesting things that's that you can do with this essentially is that you can look at these functions and their covariance between functional outputs for different inputs and see what happens and basically get like a covariance for these different outputs. So the gist is that some work by Jim Halverson and collaborators basically went through and looked at a variety of different activation functions in the infinite width limit for a single layer neural network and calculated their covariances between between a function at different outputs. And so I have a corner plot here of this for a ReLU activation with 120 nodes and one hidden layer. And the idea is that we look at it in terms of the correlation coefficients. And this is the calculation that they have here.
I'm not sure everybody can read what is the X and Y axis here.
Oh, on here.
Values of X.
Yeah, so here, these are the different values of X ranging from negative 1.5 to 1.5, and same on this axis. The gist basically being that for this particular covariance, this parameter theta is determined basically by the sign of the product between two different inputs. And that leads to basically two results. If you have a positive product, you're going to get very correlated plots on the corner plot. And if it is a negative product, you're going to get no correlation. And so that gives you a very, very weird Gaussian process. But the other thing that's kind of interesting is that as you increase the depth, as we were talking about before, we see the introduction of changes in the coupling. As you go and increase the number of hidden layers to 2, and then to 4, and then to 8, you keep increasing them, you introduce correlations that weren't there before. So that kind of furthers the perspective that as you widen it, you turn off interactions. As you go deeper, you introduce more. And then there's been some other work because Gaussian processes are very, very important to machine learning. The idea is choosing an activation function that can give you something that looks like an RBF Gaussian process kernel in the infinite width limit. And this is something that I've been working on with Dick very recently. But the idea is that as we move away from X equals 0, though, these distributions, which are initially Gaussian, start to get more like student T-like, they become more non-Gaussian. And so the thing that actually ends up happening is that the threshold for central limit theorem to kick in starts to grow very, very rapidly with X for this given activation function that gives this kind of RBF-like plot. And so what it kind of shows is that if you're looking at Gaussian process kernels and looking at that infinite width limit where we start to get these Gaussian processes, we have some dependence on our activation function of when the infinite width limit actually starts to kick in, which is kind of interesting. And so the kind of bigger takeaways here is that when we're going to build a neural network, what we want to do is we want to make sure that the ratio of depth to width should be small so that we can do this critical analysis. We want it to be bigger than 0 because 0 is the Gaussian limit, but we want it to be small enough that we can start to do perturbation theory with running couplings and only have a limited number of running couplings so that we can tune these to stable relevant things. The other things we got to do is pick activation functions that actually emit critical points or fixed points, and making sure that when we find those fixed points that we tune our weights and biases so that we can have that fixed point behavior that we want so we can get stable training. And from this Wolf-Gruber one from earlier, we see this type of behavior basically, where in all the layers, they have a small depth to width ratio. They're using the value activation function. And this thing can be tuned criticality, whether it is or not, I don't know, because they didn't specify the weight and bias initialization. But that's something where maybe there's potentially an immediate improvement by tuning it to these proper values. So some further things that are going to be interesting. This is all pre-training. Now there is more training that actually can be incorporated. Right now we have distributions of the outputs given the data. We aren't training anything, but we'd like to include the training in the form of this object called a neural tangent kernel, which basically just talks about how a neural network's output distribution evolves during training. Like it's expressed here in terms of how that cost function that we're trying to minimize is done. And it's pretty well visually executed here where it's going from our Gaussian drawn distribution to something specific for our function. So it's going to introduce new hyperparameters like those weights and biases that we're tuning before, but now for training, so we can get further stability and look more into this kind of field theory analogy for this thing. So I'm trying to apply this to the Deuteron wave function case, specifically because these guys are looking at different types of architectures and seeing what works, but they're also initializing according to uniform distributions instead of Gaussians. They're using sigmoid activation functions, which don't have a fixed point. And they're also using real Deuteron data to do the neural network quantum state learning. So it provides a really nice test bed of what if I did the same experiment and compared it against their results, but with the stuff that's influenced by my perspective from the field theory analysis. And then some opportunities that are interesting is, we have now an analogy between neural networks and field theories. The big question is looking at a functional output the best possible degrees of freedom, or since we can use like collective fields to analyze different nuclear systems, is there a collective neural network degree of freedom, and applying that to neural network field theory or neural tangent kernel field theory. And so the last couple odds and ends are basically, I had mentioned Gaussian processes, basically looking at more stuff where we have translationally invariant kernels and other types of ways of generating Gaussian processes from neural networks. There's also been proposed this information theory approach to neural network field theory that, rather than providing kind of an error bar from 0 to 1, actually provides an optimal ratio of what the depth of what should be. That depends on whatever critical behavior of your system that you have. And so that's something I haven't looked into a whole lot. It's in the references that I have here, but it's something that interests me greatly. And then again, looking and seeing at how the infinite width limit actually manifests and how well different types of architectures admit to a perturbation treatment, or do I need to make these things wider or deeper? What needs to happen? So yeah, these are a bunch of the references here that are available for looking at the actual field theory perspectives. These are the neural network applications to nuclear problems. And that's been my talk. Thank you.
Fascinating talk. Questions, Sebastian?
Yeah, very nice, very interesting. You skipped over this table you had like a few slides back, but
Yeah.
my eye. So you say number of lattice points there in the
yes.
side. So if you mean like a spatial lattice, that really only means something when you specify the size too, and then this number of points is actually a spacing or a cutoff. That's
So
what I'm getting at.
that's the problem, is that the more I've thought about it, the more I've looked into it, and the more this paper in particular lays it out. It's not actually a spatial lattice. It's just like looking at how in a given layer, you have all of the different interacting neurons in like a 0+0 D field. So I said lattice, and then the more I thought about it, the less happy I got about it.
Can you think about it in that sense of the depth, some sort of resolution, and then again come from
That R parameter is a cutoff, if you think in an effective field theory sense.
Yeah.
So people have done a Wilsonian, approach to this.
Okay, it's the other one, it's not that one together. Or the can you like specific,
Yeah,
which is R.
So R is, go back.
Yeah, so,
Where was your R?
The depth, okay. I mean,
so the R is the ratio of depth to width.
I suppose, okay.
Because the idea being that if we're thinking about it as a cutoff, the information that we have is that as it gets wider, we're suppressing certain types of interactions, and as we get deeper, we're introducing new types of
Yeah,
correlations.
that
And
makes sense. I was
so,
actually confusing with or mixing with the depth, and that's actually exactly.
oh, yeah, okay. But yeah, you can also show that when you go to look at these different couplings, there's ways for the various different activation functions that you can show that they end up scaling with this cutoff, basically, so that you can neglect certain terms when you're looking at particular values of R.
Okay, let's take one more question. One more question before, yeah, Jane.
So you showed some results with different activation functions, whether or not they
Yeah.
have a fixed point. But you mentioned you also looked at the sigmoid function. So I was wondering if you have a list of what you consider to be good activation functions, which ones you consider.
I have the couple like ones that exist in my head that I reference a lot, but if
Like, have you looked into GLU or hyperbolic tangent?
I'm curious about some of these trainable activation functions that are
Yeah.
popular recently.
Yeah, so first thing is the hyperbolic tangent and GLU are in fact do actually have fixed points.
Interesting.
Ones that don't off the top of my head are like the soft plus and the sigmoid. I'm trying to think if there's any other ones. The thing is that this first one here, this book, Principles of Deep Learning, which is on archive, has in chapter 5 a pretty exhaustive list of the ones that admit a fixed point and ones that don't. So that's something to look at. And then in terms of trainable ones, the thing that I've been thinking, it came up actually at APS April, that somebody had mentioned, can you use the criteria for a activation function that admits a fixed point to try to machine learn one? And so that's something that's of interest. Is I don't know about the specifics of the ones that they're presenting necessarily having a fixed point, but you could in principle introduce when you're training that it has to have requirements that admit a fixed point, and that would ideally give you a stable fixed point that you can actually work with in a trained activation function.
All right, with that, let's thank Simon once again. And we will break for lunch until 1:30. So those who want to go to the cafeteria, a bunch of us will walk over there. That. Good question. Yeah, why don't you take it with you?